Chapter 2, slides 7 through 12. Now that we understand how to represent some molecules, especially the molecules that do not have a formal charge, I would like to move to functionality and representing bond line structures when there are formal charges. And we're also going to talk about a little bit more about the three-dimensional nature of drawing bond line structures. You've seen a hint of that in the previous slides. Now I'm going to talk about functional groups. One of the crucial elements to understanding organic chemistry and having predictive power about the chemistry that can occur is by understanding functional groups. Functional groups are exactly as the name implies. It is a cluster of atoms in a specific orientation or bonding pattern that function in a certain way, reactively. So they undergo specific types of reactions. For instance, one functional group is called the alkene. This is simply a carbon-carbon double bond that you can see right here in our bond line structure. That double bond is the only area where chemistry really can occur because of its functionality. So learning to understand functional groups helps us to make predictions in the future about reactions that can occur at that position. For instance, the alkene in this position, we're going to learn later in the semester, can undergo something called hydrogenation and turn into a sigma bond. So the pi bond actually goes away and we're left with just the single bond. This manipulation is going to be very important as we try to construct new molecules or design pharmaceuticals or materials in the future. Basically, planning a synthesis. We have to understand and recognize functionality. So functional groups are basically areas on a molecule that have polarity, right, to some degree, that can react, and we can do stuff with them. So I really need for you to make a set of flashcards, right? This is probably one of the few times I'm going to ask you to memorize something, and that's because this is our language. These are the vocab words. And I need you to understand that when you see this cluster of atoms oriented in the way that I'm going to show you, that is the name of the molecule. This is not something you can figure out. It's just, okay, these are names. If you have no functional group whatsoever, you just have carbons and hydrogens and they are oriented in their single form bond structure, those are called alkanes. And as I mentioned before, carbon and hydrogen don't have a strong polarity, and there's no electronegativity difference between carbons and carbons and carbons and hydrogens. So an alkane is pretty unreactive. Alkenes, on the other hand, have pi bonds. They have an extra bond between two carbons, and it's not the second bond is not a sigma bond. If you recall, the second bond is a pi bond. It's a parallel overlapping of p orbitals. So that is a weaker bond, and the weak nature of that bond allows for reactions to occur. So that pi bond will break and do something. Same goes for alkynes. They have two pi bonds, right? And so the two pi bonds are also parallel orbitals overlapping, not head-on like sigma, strong overlap, but weaker parallel overlapping. And so the weaker nature of the pi bond makes for greater reactivity. So triple bonds between carbons are called alkynes. Next, we have the oxygen type functional groups where you have an OH. Again, it's an OH off of a carbon. So this whole R, carbon OH, is an alcohol. Carbon O carbon is an ether. An amine is a nitrogen with any combination of carbon or hydrogen off of it. Now, this can seem a little confusing. I get this a lot with students. They see an OH and they immediately think alcohol. But I want you to now pay attention to the other box I have here to the right. These are all functional groups that have a carbonyl. A carbonyl is a carbon double bonded to an oxygen. Okay, that is a carbonyl. Now there are different types of functional groups that have carbonyls. A carbonyl, notice that I've got a bunch of functional groups here that all have a carbonyl in them, right? Carbonyl, 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 carbonyl. But each one of those carbonyls is a different functional group. When the carbonyl is flanked by 2 carbons, it is a ketone. When the carbonyl has at least 1 hydrogen on a side, it's an aldehyde. If the carbonyl has an oxygen carbon right off of it, it's an ester. If the carbonyl has an NH2 right off of one side, it's an amide. And when a carbonyl has an OH off of one side, it's a carboxylic acid. Now, this is where it gets a little confusing, or students get this little mixed up from time to time. Students will see a carboxylic acid, see the OH, and call it an alcohol. It is not an alcohol. So when you see a carbonyl, I want you to extend the functionality across. Think of it as one unit. Say, ooh, that's what makes each one of these the functionality name is what I've highlighted here all together. It's the carbonyl and what's next to it that make it an ester, that make it a carboxylic acid. So this is not, the OH of a carboxylic acid is not an alcohol. This whole thing is a carboxylic acid and it functions together. You can't piece it apart. An alcohol and a carboxylic acid, very different. They have very different properties. An alcohol, right, like ethanol is in beer and liquor, right? Not acidic. Carboxylic acid, if you just had a methyl group, a carbon on the other side with hydrogens, that would be vinegar. Very, very, very different attributes. So functioning extremely differently, they are different functional groups. So make sure that you can identify each one of these as they are in, say, a larger molecule. Make flashcards if that helps you in the beginning. I mean, we're going to use these a lot, so they will become second nature, part of our language, but make a flashcards for now if that helps you to memorize them. Okay, let's talk about bond line structures when we have formal charges involved. I'll do the first one with you. So far, we've been looking at bond line structures where the atoms were neutral. So we could assume all the hydrogens and lone pairs that we needed to that go with the bond trend for that atom. We also need to be very aware about assumptions made in lone pairs and hydrogens when we see charges involved on an atom. And they have to be given to you. If the charge is not given to you, you're just going to assume it's neutral. Here, we notice that in A, we see that we've got a nitrogen with a negative charge. What does that mean? Well, think about nitrogen. Nitrogen likes 3 bonds and 1 lone pair. Okay? Right now, we've got nitrogen with 2 bonds, and I have to figure out how many lone pairs it has, but it's telling me that it has a negative charge. So what that means is that there are more electrons than normal on the nitrogen. Well, normally nitrogen would have a lone pair. And so in order to gain its octet, it doesn't have another bond. That must mean that a negative nitrogen has 2 bonds and 2 lone pairs. It has more electron density than typical all to itself. Thus, that nitrogen is negatively charged. If you look at B has an oxygen and it's neutral. So it should be oxygen in its normal bond trend, which is 2 bonds and 2 lone pairs. I see 2 bonds already, so that means it's just normal. It just has its 2 lone pairs, so we're all set for that one. In contrast, look at C. C has an oxygen with a negative charge. What does that look like? Well, we know that it should have 2 bonds and 2 lone pairs. It only has 1 bond. It normally has 2 lone pairs, and so I can't draw another bond. If there was another bond, we would have seen it. So that means that it has more electron density than normal, so it must have 3 lone pairs. That's what makes it negative overall. Feel free to convince yourself and do the formal charge calculation, but as you can see from bond, if you know your bond trends, you can actually figure out how many lone pairs or bonds are there just by looking at the negative charge given, or the positive charge in this case given. Nitrogen, as we said, has 3 bonds and 1 lone pair. This nitrogen has a positive charge. It's also saying that there are 4 CH3s all around it. Now, normally nitrogen likes only 3 bonds. It normally likes 1 lone pair all to itself, but it appears that one of these bonds, it had to be formed using nitrogen's lone pair. So nitrogen had to take that lone pair it had all to itself and share it. So it lost electron density. Thus, nitrogen is outside of its bond trend, and because it had to share its normal lone pair as a bond, it is less electron dense, giving it a positive charge. So the nitrogen bears the positive charge in this case. So formal charge does affect the stability and the reactivity of molecules. So you must be able to identify formal charges in bond line representations. So I'd like for you to get used to seeing the elephant in the room. Here is a molecule where I've drawn the appropriate lone pairs and bonds, but I have forgotten to put the charges where applicable into the molecule. So for any atom that is outside of its bond trend, I'd like for you to redraw this molecule in the box with its proper charges, and you don't have to draw the lone pairs. So draw the Lewis structure for that molecule with its appropriate charges, either plus or negative where appropriate. I'd also like for you to draw the Lewis structure for H2SO4. Why? We're going to use this acid, hydrosulfuric acid, quite a bit in this course, and you're going to be using it from time to time in the lab. It's really important to know what the molecular structure is for the compounds that you're working with. So I'd like for you to try doing that right now. I'll finish the H2SO4 off for you, but I'd like for you to pause this video and see if you can do it. Just so we're on the same page, the Lewis structure for H2SO4, starting with the sulfur. What you'll notice is that the structure for this molecule has an extended or expanded octet. Let's take a look at the periodic table and see where sulfur is. Notice that sulfur is far enough down that if you do the electron configuration for sulfur, it has what? It has d orbitals. Sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. You can say, wait, it doesn't have d orbitals. It does though. Think about the 3. The first row of d orbitals is row 3. So in that shell, like this, the titanium, vanadium, chromium, manganese, iron, that whole row, that first D row is actually a 3D row. It exists for sulfur. It just doesn't have any electrons in it. It's like having a house with an attic. There's this higher up energy orbital that exists. We didn't put anything in it, but it doesn't mean that just because I didn't put anything in the attic doesn't mean that it isn't there. If your molecule, or say if your atom, doesn't have a row 3, like for instance, think about carbon. The last shell for carbon is 2. There are no such things as 2D orbitals. Therefore, carbon can never exceed its octet. Sulfur, and anything in row 3 and onward, has D orbitals whether or not they put anything in them when we do a normal electron configuration. This is why we can see an expanded octet for sulfur when you do a bond line structure. The sulfur has 2, 4, 6, 8, 10, 12 electrons all around it. This is going to be important as we talk about other reaction mechanisms in the future. But I want you to be aware that sulfur has a formal charge of 0 here, and it can have an expanded octet. You'll see this for phosphorus as well. Think about ATP, triphenyl phosphate. Try drawing that out. You'll see that phosphorus can, in many times, have an expanded octet. Why? It has 3D orbitals available to expand. Okay, sometimes carbon will have charges as well. I know I said that carbon doesn't, carbon to carbon and carbon to hydrogen are nonpolar bonds. That is true. However, depending upon the bonding pattern for carbon, carbon can be either positive or negative depending upon the situation. I need you to become familiar for when carbon is outside of its bond trend and thus bears a charge. For instance, if a carbon has a positive charge attributed to it, it means that it doesn't have a fulfilled octet. Remember, carbon likes 4 bonds. That's what it likes. No lone pairs, just 4 bonds. So if carbon has a positive charge, that means it only has 3 bonds. So when carbon is outside of its octet and it has 3 bonds, no lone pairs, it's a positively charged species called a carbocation. Here's another example. A carbon with a positive charge, but doesn't it look like it has 2 bonds? Well, it does still have 3 bonds. You guys know what that third bond is? You guessed it. It's an assumed hydrogen. So in the first case, we're seeing all 3 bonds because they lead to carbons. It's a carbon bond, carbon bond, carbon bond, CH3, CH3, CH3. There were no assumed hydrogens positively charged. In the second case, it's telling us that there's a positive charge on this second carbon in, but I am only seeing 2 bonds because those are the ones that lead to carbons. Therefore, the third bond must be an assumed hydrogen. When the carbon is on the primary, so actually we have names for these. When the carbon has a positive charge and it's connected to 3 other carbons, it's a tertiary carbocation. When the carbon is connected to 2 carbons and has a positive charge, it's a secondary. There's a 1 assumed hydrogen there. And when carbon is on the end, so you only see 1 bond, it still has 3 bonds, but 2 of them are assumed hydrogens. Because it's only attached to 1 carbon, it's called a primary carbocation. So I need you to get familiar with assuming hydrogens when you see charged atoms. Now we're going to extend our bond line structures, and we've seen this before more formally now. I just want to address the 3-dimensional nature of these bond line structures. I talked about the zigzags being kind of perfect formatting for the tetrahedral, and assuming that the hydrogens that are off of the carbon zigzag are drawn out of the plane, both forward and back. Now, if you're just talking about a zigzag and you're not drawing in the hydrogens, we don't have to draw those wedges and hash lines to represent out of the plane. But as in the earlier video from the previous slides, you'll notice that we can't draw this. I mean, if really quickly I can, but this does not show a three-dimensional nature, right? Remember, we're talking about tetrahedral here. This carbon is sp3 hybridized tetrahedral. I can't draw all of these lines. It makes, from an artistic perspective, it just looks like they're all flat. So what we're going to do is we're going to say that when we draw bond line structures, a straight line, it is going to mean flat and in the plane of the paper. So the zigzag, that's what's beautiful about the zigzag. I can draw a zigzag line because every one of those bonds can be represented as being in the plane of the paper. It's the things that come off the zigzag, if the carbon's in a tetrahedral format, that can't also be, you can't have 3 or 4 bonds all in the plane of the paper and expect us to see, oh, that looks like a tetrahedral. So we've adopted these ways to represent coming at us or up and going away from us, like the disappearing hashed lines or dashed lines going back or away from the paper. There are, even when we draw cyclic structures, you can see that things can be forward or coming at us, or hashed or dashed and going away. There are a lot of different ways to represent three-dimensional nature of these molecules because these molecules are not flat, as you see from the models. I'm going to draw this bicycle in a way that represents these atoms, carbon 1 and carbon 2. So you can see this is like coming at us. It's like a three-dimensional. I'm shading it so that you guys can see what's in the front. Carbon 3 is a bridgehead carbon. Carbon 4 is up at the top, coming out at us. Carbon 5 is the other bridgehead at the other side. Carbon 6 with the up bromine. That means the hydrogen is down. And carbon 7 is with the down methyl with the up hydrogen. So these are tough and they take practice. We'll work through a few bicycles much later, but I just want you to understand that these tetrahedrals, trigonal planars, all of these geometries, we're teaching them for a reason, and they have representation when we draw. So understand what the wedged, solid wedge, and dashed wedges mean, coming forward or up, going back or down. I can also do the show you different orientations of the same molecule. So what I want to show you is that when you're drawing the zigzag, it's important to understand that when you do hashed and wedges, you do them on the same side. So again, think about what tetrahedral means. It means that we have electron clouds and they're trying to orient away from each other in such a way that everyone has as much elbow room as possible. We don't want the clouds being close together because the electrons will repel. Tetrahedral orients them through space in the perfect scenario, but when you have 4 electron domains around a central atom. So what I don't want you to do is what I have in red here. You do not put something between the acute angle here, because that's not the best place for something, right? You want to put it in the obtuse area. spatially away from one another. So don't draw things in this acute angle. Draw everything in the obtuse area. Make sense? Okay, here we have an example of a molecule where you have a carbon, a tetrahedral carbon with a bromine, chlorine, hydrogen, and methyl. If we represent each one of these as the bromine in red, the chlorine as green, the carbon as blue, and the hydrogen as white. Okay, I can show you three-dimensionally using a model that I'm not going to break any bonds, but you can see that the methyl and the chlorine are in the same plane as drawn by the straight lines, and the bromine is coming out at you and the hydrogen is going back. If I switch from one orientation to the next one, I put the methyl up to the top. The chlorine is in the same plane as the methyl, but to the left. The bromine's coming out at you and the hydrogen's in the back. Now notice for all of these top row, the methyl's up at the top. So the change from one to the next is simply just rotating the molecule to show a different perspective. All of these are a correct way to draw it. It's confusing though, right? Because they're the same molecule, but they're drawn differently. This is like walking to a statue, right? Walking up to, maybe even walking up to, a big statue in the middle of the room, right? And your perspective is you walking around it. So if you're walking around a statue of a human with outstretched arms, as you walk around it, the perspective of those outstretched arms sometimes are going towards you. Maybe if you walk to the back of the statue, the arms are away from you. So your perspective is changing, but the molecule isn't moving one bit, right? Your perspective is changing. At the bottom here, I'd like you to try and place a forward methyl group, CH3, and a back or away from you chlorine onto carbon number 3 below using wedged and hashed lines. Lastly, I'll mention that there are many other ways that you're going to see three-dimensional bond line structures drawn. I showed you the bicycle configuration in the previous slide. There's also a couple more. We're going to learn about Fisher projections a little bit in an upcoming chapter when we do stereochemistry. And you'll also sometimes see these Hayworth projections, especially in carbohydrate chemistry. These are used together in carbohydrate chemistry, and we'll touch upon them as they become relevant or contextual to the context that we're talking about. But I just want you to be aware that bond line structures, the way that we've just been looking at them, are what I'm going to use for the majority of this course, but sometimes you'll see them represented, or three-dimensional structures represented like I have here in either Fisher or Hayworth, but they will be a minority of the time.